धर बेटा. किती वाजता येणार? टायरवाला घरी येऊन घेऊन बदलून जाईल का? नाही, पण त्याला हे करायला लागेल टायरवाल्याला. अगं नाही ग.
Thank you. Asminam, thank you. I'll continue.
Thank you. I leave.
Okay. Any other member is joining?
Sir, good morning, sir.
Good morning. Good morning.
Sir, what topics are today? Which
So we
topic?
are discussing today cooling tower,
Cooling tower in book 3.
book three.
Cooling tower.
So we shall start. Good morning, all. So we'll discussing today on cooling towers. So it's the most important and most neglected topic in any industry. So not in the BE exam, but in any industry. So cooling towers are placed in somewhere around the corner, but their job is not to job is the most important job in any process industry, like many pharma factories, then chemical factories, they rely mostly on cooling tower. If your cooling tower performance is bad in some manner, or it's not working properly, your entire energy scenario changes, because the dependency on cooling tower is too much. Like uh, whatever energy balance you are doing, or energy, if you want to find the energy balance of your factory, how much energy is consumed in terms of electrical, in terms of steam. So you can find it out from the cooling tower. You can start reverse engineering and you can find out your energy consumption from cooling towers, because that's how important this topic is, or that's how important utility it is. So what cooling tower, like you all are from industrial background, so you assume, like I assume that you have seen multiple cooling towers in from right from a cooling tower application, right from your HVAC application, then process heat rejection. Then there are a few machines like induction heating machines and all this. So they all require cooling towers, and that particular cooling tower reject all sort of heat, or reject all sort of wasteful heat, or we can say process heat into atmosphere with the help of whatever like whatever constructed material, or material is available with them. So basically, if you see any power plant also, their major performance improvement parameter depends on your cooling tower, cooling water temperature, or cooling tower performance. So if you want to improve your yield on power plant, but if you want to improve turbine yield or turbine energy improvement, so you need to improve your cooling water performance, or you need to circulate more water into system. So that's how the important role of the cooling tower is in industry. So basically, what we'll cover today is basics of cooling tower, then evaluation studies for cooling tower, what are the methodologies, or how to calculate the cooling tower performance and all these things. Then we'll definitely see energy conservation opportunities, what are the energy conservation opportunities, and then we'll look into a case study for energy savings in cooling tower. So, what is cooling tower? So, like you have seen cooling tower in multiple applications. That cooling tower is useful for removal of heat, or removal of heat from process, removal of heat from equipments to the atmosphere. And what is the principle behind that. So what does cooling tower, a typical cooling tower looks like this, like a blue one is a typical cooling tower you can see across any industry, or you can see in many other industry. So this is a typical cooling tower, and this is a thermal power plant or power plant based cooling tower which is constructed from a civil structure. So typically, what does cooling tower do? There is a inlet water attached to the cooling tower. On the top of it, the water splashes, and the water falls on the any surfaces. So surfaces might be fields, surface might be honeycombs like structures, and all this is the water falls on that particular surface, and it gets contacted in with the air, and ear suction is done from this side. So this ear is getting suctioned here, and with the help of that particular fine atomization of water, so fine that is sprinkled across the fields and media. So the fine atomization of particle has been done, and the air flows in the cross direction. So they got in contact with each other, and the heat is getting transferred. So, this is the one mechanism. So where your water is finely atomized, and it can get maximum surface area, and the all heat is accumulated heat can be rejected through the to the atmosphere. So the major dependent parameter, or the main parameter of the to decide a cooling tower performance is your ambient air. So ambient air means what are the conditions you are placing your cooling tower in, what are the what kind of atmosphere you are providing to the cooling tower. That is more stricter thing, or more we can say a critical thing in your cooling tower performance. So if you are providing if you are providing ambient air, not too much, or not you are providing a cooling tower in enclosed area, or you are covering it with other mediums, or like I have seen multiple examples where people have barricaded cooling tower with the green shade. Why? Because the dust particle and all these things falls in that particular cooling tower basin and all these things. But really the air quantity whatever is required to do a better performance, so it is not provided. So that's how critical location of a cooling tower is much important. And why it is dependent on your dry bulb and wet bulb. So you can, without any mechanical work done, you cannot cool your water below your wet bulb temperature. So if you want to cool that water below your bed bulb temperature of air, you have to do a mechanical work. Mechanical work means you can use a compressor, or you can use a chiller, so to reduce the temperature furthermore. But if you don't have to do a mechanical work, you can limit your water to the bed bulb temperature of ambient air. So means if you are having a condition of, let's say, 35 degrees Celsius in 35 degrees Celsius, and our bed bulb temperature is around 28 degrees Celsius. So you cannot cool your basin temperature, or you cannot cool your process water below 28 degrees Celsius. It's thermodynamically not possible. So 28 degrees Celsius is your limiting factor. So, but if you are not getting that 28 degrees Celsius, or if you are not achieving that 28 degrees Celsius in cooling tower, so there is a problem. If you are getting a process heat of, let's say, inlet process water around 33, 34 degrees Celsius, and you are not cooling it beyond till 28 degrees Celsius. Basin temperature is not 28 degrees Celsius. So your performance of cooling tower is mismatched, or performance of the cooling tower is not that like great, we can say. So these are the deciding mechanisms. So likewise, operation is all totally dependent on your ambient air temperatures. So there might be an situation like the same same model, like let's say a 200 TR machine is supplied in Pune. I'm giving an example, supplied in Pune and supplied in Mumbai. The performance of the Pune chiller and the performance of the Mumbai chiller, irrespective of whatever compressor, whatever parameters they are providing, the same parameters, their performance may vary due to the performance of their ambient air, ambient temperatures. Because the ambient temperatures decides in the Mumbai, you can see that there is a humid temperature, and in Pune it's majorly dry temperature. In monsoon, like in summer or summer, your Mumbai temperature is quite humid, and in Pune temperature it is dry temperature. So their performances, irrespective of your same configuration, may vary according to their ambient air, because the cooling tower is directly connected to chiller condenser, and chiller condenser is major deciding factor on the performance of the chiller. So that's how the ambient air performs the role, or perform the its own it has own its meaning. Then we'll go to the applications of cooling tower. Applications of cooling tower, we have discussed. Like one of the application is your power plant application. So means in power plant there are multiple type of turbine, like condensing turbine would be there. There would be back pressure turbine. Majorly the cooling towers are used in condensing turbines, where your some part of the steam is condensed and it is cooled with the help of your cooling tower. And that condensing turbine, if your temperature is on a higher side, cooling water temperature is on higher side, so your turbine performances goes down. And turbine performances goes down means your yield or output kilowatt hour or output power generation goes down. So that's how the important is your uh, cooling tower in a power plant. Then there are HVAC or process chiller application. HVAC means your chiller application. Then you have a process application, like many of the reactors, many of the multiple effective operators. Then distillation column requires condenser cooling. So that condenser cooling is with the help of cooling tower. Then another application is your induction furnaces. Nowadays, majorly in automobile, induction furnaces are used, and that induction furnaces rejection of heat is done with the help of cooling tower. And that is mandatory to provide a cooling tower to the induction furnace, because that induction coil cannot withstand that particular, cannot go beyond certain temperature if you are not rejecting heat to the atmosphere. So that's how the application of cooling tower is important. Then other cooling applications are electrical panel cooling can be done with the help of this cooling towers. In the majorly electrical panel cooling is done in induction furnace only. So these are the some applications of cooling tower. So when we'll see the type of cooling tower, one is your natural draft cooling tower and one is your mechanical draft cooling tower. Natural draft cooling tower means if you are seeing this natural draft cooling tower, this is your natural draft cooling tower, where your natural draft cooling tower is uh, provided with the help of your concrete structure, and concrete structure majorly is in the parabola structure. So that helps in airflow, and that natural draft cooling towers are majorly used where your water flow are beyond 45,000 meter cube per hour or larger application. They are used in natural cooling towers. Then This typical height of the cooling tower is around 350 to 500 feet. With the help of that particular height, they are able to cool. They are able to cool that particular inlet water. So these are some applications of natural cooling tower. Then another application of cooling, another type of cooling tower is mechanical draft, which is widely used in industry. So mechanical draft means you are providing a mechanical ventilation or mechanical air circulation with the help of that particular uh, fan or blower, we can say. So this is your fan, this is your fan, this is your fan. Then another is a centrifugal fan provided. So in the mechanical draft there are three types again. Three types. One is your induced draft counterflow tower with the fill. So induced draft means here is your induced draft. Then counterflow is your cold water, hot air comes in this manner, where your fields are located below this spraying of water, and air comes inside the cooling tower at the bottom near to the basin. So air passes from this to this, and this is a cold air or ambient air, and after the surface of the hot water, it gets heat is transferred to the air and it gets circulated to the atmosphere. So it is a induced draft counterflow. Counterflow means water flows from top and your air flows from the bottom. So there is a counterflow between air and water in this, and the cold water is collected in basin and then circulated to the again system. Then again, your next type is your induced draft double flow cross flow tower. Means induced draft is there, then double fills are provided in the side of the cooling tower, and this fills water is spread above the fills, and both of the airflow is from beside the fill section. So louvers are provided in the beside the fill section, and the water is circulated to cooling tower from fills to the atmosphere. So it's a induced double flow. It's similar to the cross counter flow, si- similar to the counter flow, but it's a double fill structure. So hot air distribution is above from the top of the system. Then forced draft counterflow tower. So counterflow towers means your fan is not provided on the top. Fan is provided below the in the cooling tower. It's a centrifugal fan, and the air flows from fan to then again water splashes, and then it goes to the top of the cooling tower. But this kind of cooling tower you will see majorly. So 60 you will see this kind of cooling tower, and then few of the cooling tower might be this like this would be there. This is the typical power plant applications.
Sir, one question, sir. The
Yes, sir.
fan is there in both induced and forced drafts also.
Yeah, induced and forced draft is same only, sir. So yes, induced and forced draft, both of the fan. But in the induced fan, it's a we can say axial fan. In the forced draft, it's a centrifugal fan.
Oh, in the forced draft, fan will be in the bottom. Acha, acha.
Yeah, fan will be at the bottom, and it will be a centrifugal fan. But in the
Induced draft.
induced draft, your actual fans are provided.
But what we are saying in HVAC systems, no, those fans are provided on the top only.
In
That is
HVAC system,
HVAC system of cooling towers. I mean,
yeah. But I also said that 50-60% you will see this type of cooling tower only.
with induced draft.
Induced draft counterflow cooling towers.
Counterflows. Okay, okay, sir. Thank you.
So they are widely used. You can say you can get your cooling tower from 20 to 30 TR to let's say 500 TR, 600 TR. You can get any size of cooling tower in the induced draft counterflow type. So
Oh,
fans might vary, like in 1000 TR cell, there can be a. This is the one live example of a cooling tower. So this is the cooling tower.
Yes.
So they are interconnected. They are interconnected. They are directly connected with each other. So they act as one cooling tower, but they are different cells. We can say different cells. Fans are different, but they are one cooling tower only.
Okay. Okay, sir. Continue, sir. Then.
Yeah. So these are the some types of cooling tower. So you can get a single mark question or MCQ on the type of cooling tower, where this natural draft cooling tower used at from what water flow it is used. So typically water flow is around 45 to 50,000 meter cube per hour, and they are majorly used in a power plant. These are the some general typical applications of cooling tower, mechanical draft are typical applications. So you can get this single liner on these particular types of cooling towers. Then we'll see the construction or components of an industrial evaporative cooling tower. Evaporative means it is a methodology of heat transfer. So it's a evaporative cooling type of cooling tower. It's only evaporative means you are provided with larger volume, larger cooling tower is basically a desert cooler. But desert coolers are majorly used for your this majorly they are used for your comfort conditioning, but they are the application is safe. So your water carries through with the help of that particular water, particular year. So construction components means what are the components? So casing is your entire frame or support exterior enclosure is called as casing. In which this is casing. This is the casing of cooling tower. Entire is casing of cooling tower, in which your fan, lures, fills, all these things are attached in the cooling tower casing. Fills is the fills are the some surface fills are the some medium which provides maximum heat transfer area, and they are maybe splash type or film type. We can see the type of the fill, but they are majorly used to provide maximum heat transfer area. You have seen the heat exchangers in your industry. So the typical heat exchanger are made of metallic structure, but their work is same. You have to provide a maximum heat transfer area in that particular to get maximum output. So they are compacted. They are used as a radiator or heat transfer mediums. The same fields are used in cooling tower. Some not metallic, but same principle is there. Then cold water basin. So majorly cold water basins are used for collection of cold water at your bottom of the cooling tower. So whatever hot water is circulated at the top, the cold water is collected in the bottom, and then again it is recirculated to the system. Then eliminators means in larger cooling towers where drift eliminators are used to avoid the evaporation loss. Some of the water there is an induced fan at the top of the cooling tower. So water tries to escape from the cooling tower, and that is due to the temperature, vapor pressures. So it is causing a evaporation loss. And that particular to avoid that evaporation loss, the drift eliminators are provided. So how they are located? They are located at the top of the cooling tower, where your drift or your water vapors try to escape. So you try to provide an area where they can condense and then again come to the cooling tower system, because it's a water loss. Evaporation loss is a water loss. In the cooling tower, it is the loss where your water to always keep your makeup on, means makeup water on due to evaporation loss and this methodology. Then evaporation loss, there are cycles of concentration or blow down losses are there. So we'll see the losses again, but it's a drift limiters are used for excessive evaporation, reduce excessive evaporation loss. Then air inlet means where your air is getting inletted. So these are the some kind of uh, frame, or we can say a mesh like structure provided to get a air inlet in the sensor. People nowadays used to uh, many in many industries people used to cover this with green net and all these things. So this is a wrong practice followed in industry. Then nozzles. Nozzles means where your water spray occurs. These are the some nozzles. These are the nozzles of a cooling tower where your water is circulated from the pipeline, and these nozzles create a additional pressure, and uh, uh, it sprays according to your it atomizes the water and it sprays on the fill. So nozzles are mandatory in the cooling tower, because if you give direct pipeline and direct water flow, it will be water flow will be an direct laminar flow. But if you provide a nozzles, you can splash it like a shower or like thing. So nozzles are mandatory, and the nozzle choking, nozzle cleaning exercise should be done in cooling tower. Then fans are generally a propeller type of fans used in indoor cooling towers, where you want to create a pressure and you want to suck the air from the bottom of the tower to the exhaust the hot air to the atmosphere. So fans are provided in the cooling tower. So these are some construction or components of the cooling tower. Then performance, what are the type tower material can be multiple towers are made of FRP. Then multiple towers are made of nowadays they were previously they were using wooden cased cooling towers. Nowadays days they have shifted it to the FRP kind of thing, and all the material and all this material is provided with the low maintenance and reducing the corrosion. They have provided this FRP material. Previously, what happens when you provide a wooden cooling tower, after a certain year of operation, the fungal or fungi algae growth was there, and algae growth causes another problem of blowdown has to be there, or the cycle of concentration has to be there in your cooling water again and again. So the water quality deteriorates. So nowadays they have shifted to FRP. Many use nowadays they are going for. So what are the performance definition, or how the performance is calculated in the cooling tower? So if you see this example, or if you see the baseline, so your water temperature is coming inside the cooling tower. Assume this is a cooling tower. What water is coming inside the cooling tower, and your cold water is going outside the cooling tower. Difference between hot water and cold water is called as a range of cooling tower. Range of cooling tower is always in degree Celsius, wherever inlet temperature might be a 34 degree Celsius and outlet temperature 29 degree Celsius. So your range of cooling tower is 5 degree Celsius. So these are the some typically your cooling tower is defined in the range parameters. Like I want a cooling tower of let's say 36 to 32 degrees Celsius. So 4 degrees Celsius is your delta T. It's called as a range of cooling tower. So difference between inlet temperature and outlet temperature is called as range. And another is well called as approach. Approach means your cold water temperature outlet, whatever the outlet temperature would be there, and your bed bulb temperature of inlet air. So means if your water outlet temperature is 29 degrees Celsius and your bed bulb temperature is 25 degrees Celsius. So your approach is around 4 degrees Celsius, 29 minus 25. So you can cool that particular water to 25 degrees Celsius, but it's not possible due to the size of the cooling tower, lower size of the cooling tower, not proper circulation of the water flow was whatever was required. So that can be reasons of bad approach, but the approach can be minimal. So nowadays people with people takes a cooling tower with lower approaches like 2.8 degrees Celsius is nowadays a trend in cooling tower purchase. So 2.8 degrees Celsius. Previously it was 3.2 degrees Celsius. Nowadays the people are reducing to nearest temperature. So their performance of the cooling tower would be increased. Then the cooling tower has no efficiency kind of parameter because there is no mechanical work done in the cooling tower. So the cooling tower is defined in terms of effectiveness. Heat exchanger like effectiveness is defined. So effectiveness is a ratio of range. Range is this range upon range plus approach. Range plus approach means total temperature difference. What was possible. So temperature difference was possible from inlet to this temperature. So and this was typical your output, and this can be was possible output. This was possible output from 32 degrees Celsius. You can cool down to 25 degrees Celsius or 34 to 25. So you are possible of 9 degrees Celsius, but you were able to only do 5 degrees Celsius. So 5 by 9 is your effectiveness. Somewhere around say for 50 to 60% you were able to do the effective work. So that's how cooling tower are defined. Means you was able to do a 9 degrees Celsius delta T, but you were able to get only 5 degrees Celsius delta T due to some parameters, due to some other phenomena in cooling tower. But that's how effectiveness is calculated. So there is no loss. We can say there is no loss of work or no loss of power in this phenomena, but there is loss of effectiveness. So loss of effectiveness will result in other work, but the cooling tower is not like loss of power, or let's say direct power is not lost in the cooling tower. Then L by G. L by G ratio means liquid to gas ratio. So liquid to gas ratio means your water is flowing inside the cooling tower is a liquid. So it's a ratio of liquid to gas. Gas means air. Air is passing through the cooling tower. So that particular ratio of liquid on gas is called as L by G ratio.
How the air quantity is calculated in that case?
You can calculate it the help of anemometer at the exhaust or inlet. One methodology is that. Then you can calculate it with the help of whatever data of that particular fan is available with you. Like there are these fans are defined on the term of meter cube per hour, and your ratio of water is around meter cube per hour. So you have to measure that air quantity.
Is air passing through that fins or
So whatever there is only possibility whatever air is coming inside this cooling tower from these openings. So it is passing through the fields and getting exhausted at the top of the cooling tower only. There is no other opening at the cooling tower. So
okay.
you can either measure here in the openings, or you can measure at this opening.
So from calculation of L by G, what we are expecting? Which
So
parameters?
what is how the effectiveness of the cooling tower is affected. So if your cooling tower is performing only 50%, why it is affecting? If your liquid is on higher side, your gas is on lower side, why is the phenomena?
Okay.
So you can get the cooling tower analysis in the this particular L by G ratio. L by G ratio can be typically calculated from the thermodynamic side of the thermodynamic side also. H2 minus H1 is enthalpy of outlet air minus enthalpy of inlet air divided by T1 minus T2 means your range. Enthalpy of outlet air minus inlet air upon range you can also calculate. If you don't have access to the air flow, you can calculate it from the enthalpies of temperatures. You can get a temperature in cooling tower easily, but if you are not having equipped with air flow meter, and if you don't have any let's say rated data available, So you can calculate it by a thermodynamic method also.
But in case of chilled water, we are calculating the condenser water in and out. The
Hmm.
purpose of the cooling tower, basically. What is the condenser water in and what is the condenser water out?
So in the cooling,
Performer.
what happens when sorry, please continue.
So the performance is based on the delta T. Suppose I'm the hot condenser water in is 32 and I am getting
Hmm.
28,
Hmm.
like that. So in L by G ratio, what we are getting means what about the performance of the cooling tower?
L by G ratio is definitely for the cooling tower only, not for the chiller application. So if we what L by G ratio indicates, L by G ratio is a ratio between air and water quantity only. So that indicates your effectiveness. Why effectiveness is poor? If your liquid ratio is too high, liquid if you are circulating too much liquid in the cooling tower and gas is not adequate, your L by G ratio should win on higher side and your effectiveness was on lower side because if you circulating too much water inside the cooling tower you will not get able you will not able to cool that particular water because the quantity handling quantity of that particular cooling tower is lesser side but you are circulating more water inside the cooling tower so you will not get desired output desired range will not be achieved you will get 2 degrees celsius range 3 degrees Celsius range, but it was designed to have a 5 degrees Celsius delta T. So
Okay.
your range drops in that
Yeah,
particular. Yes.
understand.
So L by G ratio is that critical in to identify what are the troubles in your cooling tower. So in HVAC application, what happens when your your chiller is working? So what happens in chiller? Your chilled water chilled water is gaining some heat from the process or AHUs or something like that so that chilled water is circulating in the evaporator and that evaporator is chilled water is or evaporator water or chilled water is heat is removed in your refrigerant side heat exchange happened between refrigerant and your that particular chilled water and that refrigerant heat again is transferred to condenser the condenser is provided with the chilled water cooling water means cooling tower water so that heat is rejected from your chilled water is absorbed by the refrigerant and refrigerant heat transferred to the condenser so that's how cycle performs. Your cooling water is much critical in this particular phenomena. Means if you are providing higher inlet temperature, you will not able to do better heat rejection. So compressor has to do more work. So your if compressor is doing more work, your condensing temperature goes up, condensing pressure goes up, and condensing temperature goes up. And if your compressor has to do more work, it will consume more power. So entire chiller application, chiller performances goes down. So these are some performance definition terms in cooling tower. How the heat duty is calculated in the cooling tower. You have a flow rate, what is flowing inside the cooling tower. Then CP of water is 1 and delta T, the range of cooling tower. You are, let's say, your inlet is 32 and you are getting 28. So 4 degrees Celsius is your range. 100 m cube per hour is your flow rate. So that's a 100 into 1 into 4 so it's calculated uh, from the this particular heat duty is calculated of the cooling tower. So these are some performance definition terms. So these are some energy audit instruments are used in your cooling tower performance evaluation. So this is your power quality analyzer or fan power measurement equipment. Then airflow measurement is done with the help of anemometer. Then ultrasonic flow meter is for the flow measurement. Pen type thermometer is used for the to get accurate temperature of the waters, inlet water, outlet water. And then ceiling psychrometer is used for your ambient air temperature or exhaust air temperature, getting the ambient and exhaust air temperatures. It will give you DBT and it will give you WBT. DBT is your dry bulb temperature, which is you feel or you see 32 degrees Celsius, 38 degrees Celsius. What is the temperature of outside? So 38 degrees Celsius. And this is a ambient the dry bulb temperature, and wet bulb temperature is your humidity with the help of humidity or water molecules in the air. So you will temperature WBT is on the lower side. So this is a indicator of your relative humidity in the air. So you will get uh, temperatures from this. You will get all the data with the help of these instruments. So these are used in your energy audit of a cooling tower. So you can measure this is your cooling tower, you can measure air velocity at this exhaust point. Then you can measure the power of that particular fan. Then temperatures of inlet here, some water you can take the air and inlet water here, and then you can measure the ambient here, ambient air, the temperatures here, and then exhaust air temperatures here. So all the equipments are used to evaluate the cooling tower. Till now, any doubt in cooling tower?
Sir, I have just one question.
Yes.
Suppose in the cooling tower, if I don't get the delta T, that
Hmm.
ideally it should be 5 degree, then what will be the probable reason?
So if you are not getting a good delta T, so there might be two, three concerns. One is your probable, one is your L by J ratio is L by J ratio. You need to check the first L by J ratio. From that L by J ratio, you will get to know what is the liquid quantity, what is the gas quantity flowing inside the cooling tower. What first probable reason can be your choked fills first. Then another your water quality. Your nozzles are not spraying that water in the cooling tower as per desired conditions. Then another probable reason can be a water quality. You are not maintaining the water quality as per your it has to be maintained. You are maintaining too much TDS in the cooling tower, so your nozzles get choked at that particular mechanism. So that's how performance of the cooling tower drops. Another major, just a moment, sir, I need to put my charge. Another probable reason of the cooling tower performance is you are not maintaining liquid and gas ratio as a standard, or what was typically desired by J ratio. Means you are circulating too much of air, you are not circulating too much of water. So your cooling tower performance is going to deteriorate.
Yeah, okay, sir.
Yes. So the one more important parameter of the cooling tower is your water balance. How the water balance, or what are the losses in water, or there is only loss in cooling tower is only water loss. So water loss means your water is getting evaporation, or uh, that particular water is getting evaporated. So evaporated, then another loss is your blow down loss or windage or drift losses. So what happens in evaporation, where your when your water temperature goes on higher side, and you are atomizing fine and fine, then your that particular water quantity or water molecules want to evaporate. One means it gets evaporated in the atmosphere. So that is one of the loss in cooling tower. Then there is a formula to calculate in that particular evaporation loss. So that is zero. There is empirical relation between to calculate that is equal to 0.0085 into 1.8 into circulation rate into range of cooling tower. So you need to like understand the formula. So 0.0085 is your latent heat of evaporation at that particular for that particular water quantity, and 1.8 is your evaporation quantity for any every 10 lakh kcal 10 lakh kcal heat rejection, and your circulation rate is basically water flowing through the cooling tower, and range is temperature difference between uh, inlet and outlet. So that's how your evaporation loss is calculated. That's how your evaporation losses are calculated. So this evaporation loss will results in your lower water quantity. So you need to always make up that evaporation loss, what is evaporating, and you need to always make up in this particular to maintain your desirable water quantity inside the cooling tower. Then COC is one of the important term. COC is cycles of concentration. Means whenever your cooling to water is circulating again and again, it's a closed loop system. It's circulating again and again. There is bound to be happening of dissolving of salts inside the water, and that particular concentration goes higher and higher. So it what happens? It increases your risk of contamination to the process side. So if you are passing higher dissolved water inside the condenser of the chiller, so your chilled over that particular tubes can be filled with the help of this TDS or increased TDS. So that particular COC has to be maintained. That TDS level has to be maintained. To avoid that TDS level, what parameter is there? You need to give the blowdown. Blowdown means it's a removal of water or removal of salts from the system. So blowdowns are typically given in cooling tower in boilers to avoid the risk of contamination or risk of failure with the cause of this particular salts. So cycle of concentration means it's a ratio between your makeup water dissolved solids to the ratio of dissolved solids in circulating water to the makeup water ratio. Means makeup water will also have a TDS, sort of TDS. So your water from the cooling tower is always passed through the soft water, or is called as soft water, or it's unprocessed water. It's not the normal water you pass through the cooling tower. It's soft water after you soften the softener resin salt to treat the water, and that is passed to the cooling tower. So it's basically ratio between TDS of that particular circulating water to the makeup water TDS. So allowable COC is ranges between 2 to 10. And how the blowdown are calculated? Blowdown are calculated based upon what is your evaporation loss divided by COC. If your COC is 5 and evaporation loss say, let's say 2 m cube per hour is your evaporation loss. So 2 divided by 5 minus 1 is 4. 2 minus 0.5 m cube per hour has to be blowdown given to the system. So blowdown can be given in once in a day like thing. So blowdowns are given to maintain the salts or dissolved solids in the circulating water. Another loss is your windage and drift loss. Windage and drift loss means there is some sort of water molecules passed through directly passes from with the help of air or with the help of exhaust air. So that is windage or drift loss we can say, or from the while dropping to the basin. So from the inlet ear opening, the water molecules always pass to the atmosphere with the help of if your winds are on higher side, or you are facing some turbulence like situation, so water is getting always passed to the atmosphere, so it's another loss in the water. So total makeup water quantity, how we can calculate? We have to calculate evaporation loss. What are the quantity of evaporation loss, then what is blow down, and what is the drift and windage losses. So the total of that is equal to makeup water. So there will always makeup water provided to the cooling tower to maintain the level of water in the inside the cooling tower or in the system.
So is there any chemical treatment required for the sump
Yeah,
water?
yes, yes. Chemical treatment required because after some certain duration or after certain time, your water is getting formation of your dissolved solids are formed. Then other is your
Algae formation is there.
algae formation is there, slurry formation kind of thing. When you are dissolved solids as a calcium carbonate, the kind of white slurry forms inside the water, and that chokes your walls chokes your nozzle operation. So all these are formed inside the cooling tower. So you require the cooling tower treatment. Nowadays what they do, and they install the online cooling treatment system in cooling tower, or the soft water is always passed with the help of softener plants and all these things. Don't know of normal water is makeup. Nowadays what happens, this is a good question. uh, if you see any commercial building nowadays, in a commercial building, your energy consumption goes on a higher side. Why they are going on a higher side? You need to concentrate on your chiller, because what happens in the many industry, many commercial buildings, there is no liquid discharge outside the industry. There is a concept called a zero liquid discharge from the industry or from commercial building. So what they are doing, they are passing your they are treating their water inside this particular premises. What they do, they
STP water is used.
STP water, they use STP water, they use ATP water, ATP outlet water, or ATP water they use for the cooling tower makeup. And what that happens when you use that STP water, so there is bound to be chances are there they can carry some of the dissolved solids inside the STP water or something, some ETP water. So there is a chances of reducing the cooling tower performances. So the installation of ultra filters or installation of sand filters, ultra filters in that particular path is mandatory. Is mandatory means to improve the performance of your system. So it has to be installed. This is one of the major breakthrough in the commercial building. If you are not using ultra filters and sand filters inside the after STP treatment or after STP, whatever STP output is given to the cooling tower or makeup, that happens due to the cooling tower performances get lowest due to this kind of phenomena. You can see your STP water or is using for the flushing purposes. You can see the yellow spots on your uh, basins, or you can see the in WCs. You can see that particular yellow spots. So that's how the all the impurities are transferred to the cooling tower, and their performances are going on higher side. Now there's many auditors or many water experts are suggesting to install this to increase the performance of your entire building. And if your building HVAC goes performance goes on a higher side, your entire electricity bill goes on a higher side, because the utility and entire your energy bill or energy bill 60% of it contributes from the HVAC system. So you can't play around that 60%. You have to be very cautious in that particular HVAC. So this is your water balance of the cooling tower. Then what is your energy balance? Energy balance means uh, how the what is your typical energy is passed or energy is transmitted in that particular system. In the water side, what happens? You passed hot water inside the cooling tower from the hot nozzles on the top of the cooling tower. Water is getting flowed inside that. There is some temperature of that particular water. There is particular temperature of that particular water, and you are getting cold water inside this sump. So heat is getting transferred. The uh, quantity of heat is calculated as mass flow rate into specific heat of a water into delta T. So this is your water side energy. Water side energy is water side heat is dissipated into air. So water side heat is carrying into the air. So it has to be equal to the air side. So how the energy is calculated? So you are getting allowing some air to pass to the cooling tower. So you have a certain condition of inlet air temperature. So there may be DBT, WBT would be there. So you have some certain set of enthalpy inside this, and you are getting at exhaust. There is a certain set of temperature and DBT and WBT. So heat is getting transferred to this particular air quantity. So it has to be equaled. Energy balance means water side heat is getting rejected to air side. So energy is neither created, it has transferred from one medium to another medium. So heat removal from water side has to be equal to the heat removal from heat accepted to the air side. So how does it calculated? So mass flow rate of the air is calculated based upon the quantity you measure, then density of that particular quantity, what was there in that particular temperature, and then enthalpy of inlet air minus enthalpy of outlet air. So it has to be equal in the energy balance. Though these are some critical questions you can be asked in numerical solving to calculate makeup water quantity and calculate the energy balance of the cooling tower. So
Sir,
heat load
energy,
estimation. Sorry,
sir,
yes.
energy balance of the cooling tower means, sir, actually just
Energy balance of cooling tower means like what is the energy, there is some sort of transfer of energy happening here.
yes, sir.
So heat is getting transferred from water to air.
Yes.
So there is no loss of energy here. So energy has to be balanced. So how much energy from water is passing to the air is calculated, and it is shown LHS equal to RHS. So you can calculate your performances from this particular cooling tower. Got it?
Got it, sir. Yes, thank you, sir.
Okay. Yes. So these are some heat load estimation or thumb rule kind of is thumb rule kinds of cooling tower requirement in your refrigeration cycle. So you will require 63 kcal per TR. That's a thumb rule, we can say. Then that is not actual, or we can say exact, but it's a thumb rule is 63 kcal per TR you will require for the chiller to have a cooling tower size. Means if you are having, let's say 100 TR means 3024 into 100, 3 lakh kcal chiller you are available. So you need to calculate 3 lakh into 63. So means around uh,
Around 180
yes,
lakhs, sir.
180 lakhs you need to have your cooling tower size. So that's one standard. Then steam turbine condenser means you will be having 555 kcal per kg of steam. If you are producing 10 ton of steam, you need to have that particular 555 kcal per kg of steam. Then diesel engine, now previously there were diesel engine with cooling tower provided. Nowadays they are normally air cooled diesel engines due to compact sizes and all these things. So they were like provided with 880 kcal per kilowatt per hour. So what was the capacity? According to that, it was selected. Then air compressors. There are water-cooled air compressors we have seen in air compressor chapter. So air compressors are majorly 129 kcal per kilowatt hour. So these are some cooling tower standard sizing of that particular heat load. Then what are the efficient operation system operation? So efficient. Give me a moment. So what are the efficient system operations? Means how you can improve the cooling tower performance or cooling side improvement of the performance. There can be some of the treatments available. Likewise, we discussed there can be a formation of corrosion due to the due to the corrosion is happening due to you are using MS pipes and all these things. So the corrosion happens inside the piping and then it is passed to the system. So there is one problem of the corrosion. Then scales are formed due to dissolved solids. Then deposits form inside the cooling tower, inside the inside that particular uh, deposit scales are formed at the your walls, your uh, nozzles. This kind of deposits form. Then with the help of that particular, you are passing inlet air inside the cooling tower, and that opening may attract some dirt, then a sand particle or airborne material inside the cooling tower that can be formed inside the cooling tower. So that's why critical location of the cooling tower is important. So nowadays what commercial buildings do, they install their cooling tower on the terrace. So this kind of deposits are not that much attracted inside the cooling tower. Then there are water side problems is your biological or microbiological forming, means your algae formation, bacterial fungi formation inside the cooling tower, and that algae formation or this formation blocks the nozzles or fills, they blocks the fills. So you can see the nozzles or water is not uniformly distributed, the channeling of the water happens inside the cooling tower, and that channeling of the channeling of the water will always result in bad performance of the cooling tower. If your nozzles are choked or some of the fins are not working, so your channeling and all these things happens. So other these water side of problems can be treated with these particular solutions. Like solutions are like online or offline cleaning. Like offline cleaning means you can drain the entire system and you can remove that entire water from the system and fill the new water every time. But this is not possible in continual operational plant. So that's how the online systems are introduced, online cleaning system and all these things. So you have seen the ATCS, means automatic cleaning system in chiller condensers. So that's how the nowadays people are introducing online cleanings. There are some online chemical dosing happening uh, inside the cooling tower or lines. Then corrosion or scale inhibitors are provided uh, inside the makeup water or inside the cooling water circuit, so that inhibits the scale formation inside. And scale is very tricky part, where your scale can be transferred from here to a chiller condenser, here to process reactors. Everywhere you can pass that. And whenever there is scale formation in any kind of heat exchanger, your performance is going to drop. Then nowadays, side stream filters are used. Side stream filters, we discussed that majorly side stream filters are used for the treatment of the STP plant, output of estimate STP plant. So that's how this water treatment has to be done. Then there are some methodology of insertion of chlorination. Then hypochlorite based chemicals are inserted inside the water. So your algae formation or biological formation does not happen inside the cooling tower. Then energy loss has to be minimum. Means if you are forming a let's say scale, or let's say you are forming any deposits on your condenser side or any nozzle, your performance is going to increase. And that performance is going to increase, you can results that particular results can be seen in not in the cooling tower, but the connected utility, connected compressor, maybe connected chiller, maybe process condenser would be there. So that performance is going to drop. So that energy loss has to be avoided in the efficient operation. Then minimum drift loss has to be there. So drift eliminators has to be there in cooling tower. If the cooling tower is not provided with the drift eliminators, the water is going to be lost, and that particular water loss will be always has to be make up with the water. Then nowadays people are preferring more doing work on cooling tower fan operation. So cooling tower, they are changing their metallic blades to FRP blades. Then they are FRP blade, they are more energy efficient, or more we can say the less power consuming equipments. Then people are doing their people are changing their fans to EC fans and all these things, or automation of fans, so on off control of fan with the help of basin temperatures. But it's a tricky job to control the fan power for fan power with the help of cooling basin water temperature. So people are doing mostly automation in this thing. So these are some efficient operation has to be done in cooling tower. So I'll give an example. You can always do or energy saving in a cooling tower, where your direct process impact or direct energy impact is not happening. Means what happens when you are controlling a fan power with the help of VFD or with the help of on off control? What happens? That temperature loss or rise in temperature of the particular cooling tower will always deteriorate your performances of that particular equipment. If you're connected to a process, let's say there is a distillation column and you are connected to a primary condenser or secondary condenser of cooling condenser of that particular distillation column, and you are providing that particular high temperature of water, your product recovery is not that much. You are not able to maintain the vacuum in the system, so your product recovery is not that much. So you are losing out on the productivity, you are losing out of the power. So if you are saving 5 kilowatt of power or for 2 kilowatt of power by optimizing the fan power, you are losing much out of there inside the utility. So you need to be very cautious while doing this kind of projects, or while suggesting this kind of projects to the any company while doing an energy audit. So we have to be very cautious to understand the application. So my always say is that auditor should be on always the design side of the process. Auditor has to be a designer prior to auditor. So he understand more of the design concerns, design parameters. So there will be some of the better suggestions would be passed to the customer, or better suggestion passed to the auditee. So if you don't know about the design and you are suggesting you need to control your fan automation should be there, and that particular fan is that particular cooling tower is connected to let's say distillation column condenser, and you are not maintaining the temperature of cooling water, your product recovery is not going to do, and you are saving 2 kilowatt of energy here, means around 20 rupees per hour, let's say per 20 rupees per hour, and you are losing 1 kg of product there. So your 1 kg of product is much costlier than your 20 rupees. That's how your process, their design, and then your audit has to be combined with any energy auditor.
Sir, I have just one question here.
Yes, sir.
Suppose if we use the VFD with the cooling tower fan, and if it is in the closed loop with the water temperature, suppose my inlet water temperature that will be sensed by my temperature transducer, and if feedback is given to the VFD, based upon that, if I can reduce the fan speed, then in that case I'm not compromising on the process parameters. So in that case, also it is not recommended.
It is recommended with the help of feedback only.
Yeah. Okay.
If you are doing feedback based system, if you are not if you are setting your feedback in the tolerable limit, means if you are setting that your basin temperature, let's say 28 degrees Celsius, your basin temperature, and you are saying that 29 degrees Celsius, your fan must set on condition, must put on condition. After 28 degrees Celsius, your basin temperature is 28 degrees Celsius, and you are not operating fan, there is chances to rise the temperature. So your the design of that particular feedback has to be very strong. So you can use that methodology of proper feedback based system.
Right. With the feedback system, we can use. Okay. Only
Yes,
we have to ensure that there should not be any compromise on the process.
100%.
Performance.
You cannot compromise on the performance of any utility. You cannot compromise performance of the any of the production. So basic definition of energy audit is achieving the savings or identification of any loss, any loss in the system, or achieving the energy savings in the system without affecting the process or production. So if you are affecting any of the process or production, your energy saving is not valid there. There and there itself it is getting rejected. So that's how many energy audits they don't succeed, or they don't their projects, whatever energy reports or energy audit reports are only kept in the paper. So that's why, because the process and production production is not considered in the energy audit report. In the energy audit, you need to be thorough about all the things happening around the around that factory, around that system. So you need to understand if you are doing a commercial building, you need to understand why building has to be pre-cooled, why pre-cooling of building is mandatory. Before, if you are having a Saturday and Sunday off, Why Monday you need to keep your air conditioning on at 4 in the morning to if your office is at 9 a.m. or 10 a.m. I have like 9 a.m. or 10 a.m. and you are pre-cooling that particular building, because if you are starting your air conditioning at 4 a.m., you will be like at 10 a.m. people will not feel discomforted there. If you are starting air conditioning at 10 a.m. after people starting coming to the office, the both loads will be there. There will be building load also, and there will be human load also. Latent load is adding. So your PCs would be on, your laptops would be on. There will be motive load, human load would be there. So both loads cannot be catered by a system. So building has to be pre-cooled. Means whatever heat gain has happened in the wall, in the terrace, in the roof, the through the your glazing and through your facade, your heat gain has to be pre-cooled first, and then latent load can be accumulated. So this is a mandatory system in a commercial building. But if any energy auditor is suggesting that you are wasting your energy by putting your HVAC on during no operation, or there were no people inside the system in the office, and you are starting your HVAC system at 4 o'clock in the morning. So you are wasting out on energy. So that's nonsense. So means you didn't understand the process, or you didn't understand that particular phenomena, and you are just surrounding yourself around the energy saving. So energy saving does not happen only with the equipment. You have to understand the entire system. So that's how your critical thinking about the system is mandatory in energy audit. So if you are replacing only IF3 to IF, you are suggesting IF4 motor, or you are using nowadays EC motor and all these things, you will be saving on equipment side, but the system will not always help with the that will not help with your energy bill or reduction in energy bill. You have to very thorough about system. If then you can suggest about more quantum of the energy savings in the entire energy audit. Then what are the energy efficient operations of cooling tower? So what are the follow recommended clearances? We have initially seen that people has to ensure that the placement of the cooling tower is very critical in the corner, in the area where no access is given, or somewhere behind the wall, or somewhere near to the basement cooling towers are provided. So that recommended clearance has to be there. There has to be some free air has to be flow from the near side of the cooling tower. So nowadays commercial buildings, people used to people are nowadays cooling towers are placed on the mezzanine, where the air volume is good. So the recommended practices has to be followed. Then cooling fan blade angle or use VSD on seasons. Like there is one methodology, when your ambient air temperature goes down, you can set your fan blade angle according to L by G. You can set your fan blade angle according to L by G, and you can use variable speed based on variable seasons. Like in the winter season, your L by G might be get different. You are in the monsoon season, you can adjust your fan blade angle, or VSD. You can put that in the system. But VSD, putting the VSD in the system, it has to be a closed loop VFD. Then it install suitable size of nozzles for the proper distribution and ensure cleaning of the same. Means nozzle cleaning, nozzle spraying has to be very critical in the cooling tower. Then optimize blowdown rate as per optimized COC. Means your blowdown has to be critical but not frequent. So your cycle of concentration, your required blowdown has to be given to the cooling tower. Then there is a multiple cell of cooling towers are in operation. The water has to be distributed uniformly. Means if you are operating like this, the multiple cells, your water distribution has to be equal. Not the one cooling tower gets more water, one cooling tower is lesser water. So your entire cells are connected with each other. If it is system of 600 m cube per hour and six cooling tower cells are there, so water has to be near to the 100. Every cooling tower cell has to be near to 100 m cube per hour. Then minimize drift losses. So eliminators has to be there. Then L by G ratio with seasonal variation. We have seen that. So with the help of blade angle or VSD, you can maintain this L by G ratio. Then energy efficient FRP blades or fans are used. Majorly now people are changing metallic blade to FRP blades. Then optimize pump operations means whatever liquid ratio is required, that liquid ratio has to be pumped to the system. If you are following, if you are getting more flow rate in the system, it is not going to help you. So your pump power is also wasting. Your cooling tower liquid ratio is on higher side. So you are not adding any value to the system. So your pump operation has to be optimized. Then cleaning of fields performance evaluation has to be done regularly. So field cleaning is the primary activity done, has to be done in quarterly or in the 6 months once. Cleaning of fields has to be done. If your fields are majorly choked or broken, you need to replace that fields. So that's how preventive maintenance has to be done in cooling tower. Then this is the third part when you move to the energy conservation opportunities in the cooling tower. So there are short-term investment is you can conduct your regular maintenance of field nozzle basin. So it's a preventive maintenance or regular maintenance practice. Then variation of fan operation based on seasons and loads. You can adjust the angles. It is a only mechanical change in the blade angle. Or if your fan is equipped with your fan is equipped with the VFD, you can optimize the you can optimize the you can optimize your fan operations. Then medium term investments are on of control, but that we don't always recommend. But if it is cool with the help of your feedback, it can be done. But BSD with feedback based system, it's majorly like a go system for cooling tower. Then FRP blades, then optimization of flow to the cooling tower. These are some medium term investments. Then long term is replacement of existing cooling tower with suitably sized and energy efficient cooling tower. What happens when you add like if there is expansion going on the project, always expansion. So you add more utilities in the cooling tower, and that cooling tower is not sufficient for all the utilities. So your all utilities suffered. So you need to thorough think that this is 400 TR and I am adding 600 TR load in the system. So it will not sum up for your entire system. So you have to be very cautious while replacement of this particular system. Then there is a fanless cooling tower. Nowadays, these fanless cooling towers are used when your spray nozzle pressure is much on the higher side. So you need not to have that particular fan in the system, and your automation takes place. Automation of that year takes place in the particular cooling towers. Then reduction on cooling tower, load of cooling tower by low quality waste heat recovery on application side. So we have seen the waste heat recovery in the compressor. So if your waste heat recovery of the compressor is done in the locally, then there will be no load on the cooling tower. So that's how the your cooling tower load is reduced. So
Sir, I have one question.
yes.
That fanless cooling tower, up to what capacity it is recommended? Is there any thumb rule?
They are majorly recommended to 400, 500 TR, not more than that.
Okay. Yeah, because we have some cooling tower around 150 TR. This height and the dimension of this cooling tower is very big.
Yes, yes.
And if I wanted to go for 400, 500 TR, the size will be again very big. So it will be not practically
No,
possible
you
for us.
can install 150 TR fanless means cooling tower 150 TR, but the height of that cooling tower is on higher side because you need to provide more area to water to so get in contact with the air.
Okay, means if the capacity is more than 400, 500 TR or more, then we should not, it should not be recommended, right? Fanless
Yes,
cooling tower. Because
yes,
the size
yes.
will be very big and practically it may not be possible.
Yes, practically it not possible. The some sizes goes on higher side. All this entire civil side mechanical dimensions goes on higher side.
Yeah, correct.
Yes.
Okay, sir.
So
Yeah,
these
thank
are
you.
some energy conservation opportunities in the cooling tower. So go to the last slide of this system. So where one heat load on the cooling tower is variable as per process requirement. So process is on for 16 hours. Cooling tower fan is on at all times. No sensing of basin temperature is the present system. No sensing of the fan in no sensing of basin temperature. So what happens? What happens in if you are not having this like you are operating this, so your process is on for 16 hours and your cooling fan is all on at all times means 8 hours it is not giving output to the system. So energy efficient system would be sense basin temperature and provide on off control for fan, and then seasonal setting may be also provided. So for that 8 hours saving, if your 5 kilowatt power is there, so you can save 40 units energy per day, and if you are operating for 330 days, so you can save upon around 1.05 lakhs per hour per year. The investment is around 50,000, so payback would be 6 months. You need to understand that process is not on for 8 hours. You can put that fan in on off condition, so there is a saving. So that's how the low hanging fruits can be captured inside the energy audit. So that's all for the session. Now any questions on theoretical part, then we can move to the MCQ.
Sir, any question will come, sir, in the exam for this, in this topic?
In this topic,
So this long answer or short answer questions will be coming.
just a moment, I'll start with the answers. So, any doubt on this particular cooling tower?
No, sir, will be getting any questions, sir, in the examination? In the, on this
No, I
topic?
didn't. Yeah, you will be having questions in this topic. So we'll see the MCQs. The type of cooling tower with maximum heat transfer between air to water is mechanical draft.
Mechanical.
Yes. So natural draft cooling towers are mainly used in power stations. In counterflow induced draft cooling towers, water and air both enter at the top and exit at the top of the cooling tower. It's false. Water enters from the top, air enters from the bottom. The range of the cooling tower is determined the connected heat load. It's a correct statement because if you are having too much hot water inside the process from the process, you will not be able to cool that in the cooling tower if cooling tower is not adequate. So it is dependent on the connected heat load. Match the following cooling tower parameters. Range means
Range is
Range has to be higher temperature difference.
higher
Means
temperature.
delta T has to be higher as always. Approach is close to wet bulb temperature.
Bedrock temperature.
Outlet water temperature is related to ambient conditions. Then better indicator for cooling tower performance is approach. Approach is better indicator. All the cooling towers are always purchased on the basis of approaches. Then cooling tower effectiveness is the ratio of range upon range plus approach.
Yes, sir.
Cooling tower reduces circulation water temperature close to ambient wet bulb temperature. The ratio of dissolved solids in circulator water to dissolved solids in makeup water is termed as cycles of concentration. Which of the following has maximum heat effect on a cooling tower performance? The fill media. Because if your fill media is not that much provided, you will get to higher temperature on the if fill media is not that effective or it's choked, you will get higher temperature on the basin side. Which one of the following is true to estimate the range of cooling tower? Range of the cooling tower means heat load in kcal divided by water circulation. So mcp delta T is there. M is your water circulation. Cp is always 1. So delta T, can you calculate delta T with the help of Q divided by M? A cooling tower is said to be performing well when approach is closer to 0, but approach is never closer to 0. That's ideal situation, very ideal situation, but you need to have better approach near to the 0. Heat release rate to the cooling tower in vapor compression refrigeration system is equal to 63 kilocal per minimum per ton. So that's we saw the typical thumb rules. Then operating temperature level in the plant or process connected with the cooling tower is determined by hot water temperature from the process. Means if your temperature also is 40 degrees Celsius, you cannot have temperature below 20 degrees Celsius because you cannot achieve that much delta T in cooling tower. Because that if you want to achieve that delta T, you need to have a bigger size cooling tower. You need to have all the sort of mechanical system in this particular cooling tower. So water temperature from the process is much critical in the cooling tower. Which one of the following fill material is more efficient for cooling tower? This is called as film. Fill is the type of that particular uh, film. Fill is the efficient in the cooling tower. Which one of the following types of cooling tower consumes less power? Counterflow full cooling tower means counterflow. You are flowing your air. Just a moment. In the counterflow, you will get lower power consumption due to the air is circulating from the bottom, so it has not that much amount of work has to be done to suction that particular air. Then L by G ratio in cooling tower is the ratio between water flow rate to the air mass flow rate. Normally, the guaranteed best approach of the cooling tower is 2.8 degrees Celsius. Now they are claiming. Previously, it was 3.2 degrees Celsius. The temperature selection normally chosen on the designing of cooling tower is average maximum bed bulb temperature for summer months. So what is the summer month bed bulb temperature? It would be chosen to select a cooling tower. Means that's how the cooling tower is calculated. The fills are calculated. The size of the cooling tower is calculated. So that's how they are calculated based upon summer temperatures. Select the statement which is true for an FRP fan. It needs low starting torque. Yes, it is true. Then increases life for the gearboxes. Yes, because the weight of the FRP fan is lower. Easy for handling and maintenance. Yes, because the deposit formation, corrosion formation does not happen on the cooling tower fan. So these type of MCQs you will be asked in the exam. Then these are some short questions. There is example where they have given the water flow rate. It's 120 m cube per hour. Specific heat they have given 1 degree, 1 kcal. Then inlet water temperature is 37, outlet is 32. Ambient WBT is 29 degrees Celsius. So your range is 5 degrees Celsius, 37 minus 32. Your approach is 3 degrees Celsius, 32 minus 29. Cooling tower capacity can calculate 120 into 1000 into specific heat is 1 into range 5 degree divided by 3024. So your cooling tower capacity is near to 200 TR. If you want to calculate that effectiveness of this particular cooling tower, means 5 5 is the range, 3 is the approach. So 5 upon 5 plus 3 means 5 by 8.
So 3024, sir. 3024 is
One short ton of refrigeration.
okay. Acha.
One TR is equal to 3024.
Kilocalories. Okay.
Yes. So this kind of questions you will be asked in the exam, long answers and all these things. So there is example from the given cooling tower parameter, makeup water quantity required. You have to calculate makeup water quantity, evaporation loss, blow down loss. So they have given 12260 m cube per hour as cooling water flow rate. Then outlet temperature 32 degrees Celsius, inlet temperature 37 degrees Celsius, and number of COC they have given 3. So drift loss they have given 0.1%. Range is 37 minus 32 divided by 675. You can calculate this as a range divided by 675 into 100 as evaporation loss. There is one formula. Based on that, we can calculate evaporation loss. 0.74% is evaporation loss. Then blow down is 0.74 divided by 3 RCOC. 3 minus 1 is 0.37%. Then 0.1%, 0.74%, 0.37%. Means 1.21% is your evaporation loss. Total loss. So 1260 m cube per hour into 1.21% means your 15.2 m cube per hour is getting lost in makeup water. So these are the some numericals. You need to go through this particular numericals in the before going to the exam. You need to solve this kind of question papers. You have to do more practice before. Like we have a lecture on energy assessment of pumps. Uh, Before that, I would like to have you have to practice more on the pumps, cooling tower, and compressors. I've taken these 3 chapters for your weekend batch, so I want to have like more practice. You get more practice, get more accommodated with the writing, and do well in before your exam. So if you practice more, you're able to crack this exam. This is the most easiest exam we have seen because we have learned a lot during our engineering, during our
Next class,
diploma.
sir.
Sorry.
Next class, sir. Next class, when you take, sir.
Next class I need to check that, but I might be there will be an energy efficient energy assessment of pumps is next class on this particular batch. Just a moment, I'll check. It's 31st August. Energy assessment of water pumps. So all these numericals would be, we'll solve all the numericals in that particular class. So before that, I would like to have you practice more in this 2-3 topics. We can have a detailed discussion during that topics. Any doubt in cooling tower?
No doubt, sir. Okay, sir.
Okay. Thank you. Thank you very much.
Thank you, sir.
Stop the recording and close the lecture.